Okay, so this is problem 1. In this problem, we're told that the wavelength of the light is equal to 589 nanometers. So that means 589 times 10 to the minus 9 meters. And what we're asked to find is the photon energy at this wavelength. So to find photon energy, we're going to need to use our equation E equals hf. And then to get from f to our wavelength, we'll need to use our equation for the speed of a wave, c is equal to f lambda, which tells us that f is equal to c over lambda. So E is equal to hc over lambda. So what we can do now is substitute in. So we've got h is equal to 6.626 times 10 to the minus 34. C, speed of light, that's 3 times 10 to the 8. And lambda we know is 589 times 10 to the minus 9. So solving this on the calculator, we get 3.37 times 10 to the minus 19 joules, which is fine as an answer, but considering the amount of energy this is, it's probably better to give it in electron volts. So to convert this into electron volts, we divide it by the charge on an electron, 1.602 times 10 to the minus 19, and this has got units electron volts on joules, or coulombs if we want, and that gives us 2.11 electron volts. So this is just a more kind of familiar number that it's easier to picture than this one. Okay, so this is question 2, and I've just put a copy of the question here. So we've got the photoelectric effect for a given frequency of incident light. Which of the quantities, if any, depends on the intensity of the incident light beam? Okay, so the intensity of the incident light beam, given that the frequency is set, will be proportional to the number of photons that are landing on the target. So the maximum kinetic energy of the electrons, that does not depend on the intensity, because the maximum kinetic energy of the photons is given by HF is equal to the work function plus KE max. So KE max here depends on the frequency of the photons and the work function of the metal, but not on the intensity of the current, of the light hitting it. Okay, the maximum photoelectric current. Yes, this does. The reason this one's dependent on it is if we've got more photons hitting our target each second, then it can release more electrons. Those electrons won't have more energy, but there will be more of them released. So this one is dependent. The stopping potential, no, because the stopping potential is related to the maximum kinetic energy. So the stopping potential is what's needed to stop the electrons with the maximum kinetic energy. And as we've just said, the maximum kinetic energy does not depend upon the intensity. And so neither does the stopping potential. So no. And the cutoff frequency. So the cutoff frequency is the lowest frequency for which we can still release electrons from the target metal, and that is going to depend on the work function. So those electrons, when they're released, will have zero kinetic energy if it's at the cutoff frequency. So it's depending on the work function and not the intensity of the light. So this one does not depend on the intensity of light. So the only one which does depend is B, and so the correct answer is B. Okay, so this is problem 3. In this problem, we're told that the work function of the metal is 1.8 electron volts, and that photons with a wavelength of 400 nanometers are incident onto the metal, and we want to know what's the stopping potential for these electrons. Okay, and that's in part A. So what we know is that the energy of the incoming photons goes into overcoming the work function, and then the remainder goes into the kinetic energy of the electrons, which can have at most K max. Okay, and we know that K max is related to the stopping potential through EV stop. Okay, so what we'll need to do is put this into here, and then we can rearrange to get our stopping potential. So we've got that HF equals the work function plus the EV stop. HF, we're given our lambda. Now what we've got is this in electron volts. We'd be interested in this in electron volts because then we'd have our stopping voltage straight away. So let's work out what this HF is in electron volts. So we have HF is equal to HC over lambda, which is equal to 6.626 times 10 to the minus 34 times 3 times 10 to the 8 over 400 nanometers, which is 400 times 10 to the minus 9. So solving that, we end up with 4.9695 times 10 to the minus 19 joules. That's in joules. To get it into electron volts, we divide by E. So when we divide by E, which is E equals 1.602 times 10 to the minus 19, we end up with our HF term, our photon energy, is equal to 3.102 electron volts. Okay, so that tells us that EV stop, just going back up to this equation and rearranging it, is equal to HF minus phi, which is equal to 3.102 electron volts minus 1.8 electron volts, which is equal to 1.3 electron volts. And so this tells us that the stopping potential is equal to 1.3 volts. Okay, and then part B says, what is the maximum speed of the ejected electron? Okay, so to do that one, we're going to need to use that our maximum kinetic energy is equal to EV stop. So we've got K max equals a half mv squared, where this is the maximum possible speed. And we know that that is equal to 1.3 electron volts. Okay, so V squared is equal to 2 times 1.3 electron volts over the mass of the electron. So putting everything into SI units, we've got 2 times 1.3 times 1.602 times 10 to the minus 19. This is the charge on the electron because it's in electron volts, and that's converting this whole energy here into joules. So that's just giving us back this value here. This is that value. And then divide by the mass of the electron, which is 9.109 times 10 to the minus 31. And solving that, we get 4.57 times 10 to the 11. So that's our maximum velocity squared. So our maximum velocity is just the square root of this, which is equal to 6.8 times 10 to the 5 meters per second. And that's given to two significant figures because the 1.8 was to two significant figures. Okay, this is problem 4. Which is a Compton shift problem. And here we've got a diagram showing the shift in the wavelength versus the scattering angle. And we know that for the Compton shift, the shift in the wavelength is equal to h over mc times 1 minus cos phi. So when phi is 0, then cos of phi is 1, and the shift in wavelength is equal to 0, which is what we're getting down here. But then as the angle increases, at 90 degrees, cos of phi is 0, and so we have h on mc. Now, this h on mc is going to be larger for lower masses. So number 1 has the largest value of h on mc, because that line is above, and then 2, and then 3. So 3 is going to have the largest mass, i.e. we're dividing by the largest number, and so we end up with the smallest shift. So this tells us that the mass of 3 is greater than the mass of 2 is greater than the mass of 1. Okay, so this is problem 5. And it asks us, why was Compton's experiment important? So Compton's experiment was important as it showed photons had momentum as well as energy. And this was interesting because before this it was thought that to have momentum you had to have mass, and photons do not have mass. So photons do not have mass. Their momentum is given by P is equal to h over lambda. And so how did this change our understanding? Well, before this we thought that if something had momentum it had to have mass. Now we know that if things don't have to have mass to have momentum. Okay, so this is problem 7. In this one, we've got a nuclear fireball, and we're told that the surface temperature T is equal to 1 times 10 to the 7 kelvins, and we're asked what's the wavelength at which the thermal radiation is maximum. Okay, so this is Wien's law 1, and Wien's law tells us that the wavelength at which the thermal radiation is maximum times the temperature is equal to 2,898 micrometers kelvins. Okay, so all we need to do is rearrange this to get lambda max. So lambda max is equal to 2,898 times 10 to the minus 6. This is that micro, and then that's meters kelvins over the temperature. And now we can just substitute in. So this is equal to 2898 times 10 to the minus 6 over 1 times 10 to the 7. That's meters kelvins, this is kelvins, these cancel and we get meters, which is what we would expect for a wavelength. And we get that that is equal to 2.898 times 10 to the minus 10 meters. So we can write this, if we want in nanometers, as 0.29 nanometers. Often with wavelengths, it's nice to write in nanometers because then it gives us an idea about the type of radiation it is, because visible light's between about 300 and 800-ish nanometers. So we can see that this is a little bit shorter than visible light, which helps us for the next part, which asks us to identify the type of electromagnetic radiation. It's just a little bit shorter than visible light, so this is actually X-rays. It's in the X-ray part of the spectrum. Part C, so this is then absorbed and re-emitted, but now the temperature is equal to 1 times 10 to the 5, and we're asked, well, what's the wavelength with the maximal thermal radiation now? So we substitute into this same equation, 2898 times 10 to the minus 6 meters kelvins over 1 times 10 to the 5 kelvins, and solving that we end up with 2.898 times 10 to the minus 8 meters. So again, let's put it into nanometers because then we can relate to it a bit more easily. So nanometers is 10 to the minus 9. So this is 29 times 10 to the minus 9, or 29 nanometers. Okay, so 29 nanometers, that's again shorter than visible wavelength, but much closer to it. So this was quite a bit shorter, but this is just slightly shorter than visible radiation. So then in part D, when it asks us for this type of radiation, well, this is the ultraviolet radiation, as it's almost visible but not quite. Okay, this is problem 8. And in this problem, we need to calculate the de Broglie wavelength for a number of different particles. Okay, so the de Broglie wavelength, lambda, is equal to h over p. Now, with each of these particles, we're given their energy. So we're going to have to relate the wavelength to the energy. So in order to do that, we can write that, well, the kinetic energy, which is what we're given, is given by a half mv squared. And so this is equal to a half m squared v squared over m. And why we want to write it this way is that this is a half p squared on m. So this tells us that p is equal to the square root of 2mk. And so now we can relate our energy to our wavelength. And so this tells us that the wavelength is equal to h over the square root of 2mk, which will help us solve a couple of these problems. Okay, so in part A, we've got a 1 kiloelectron volt electron. So lambda is equal to h over the square root of 2mk, which is equal to 6.626 times 10 to the minus 34 over the square root of 2. Now it's an electron, so the mass is the mass of an electron, and that's equal to 9.109 times 10 to the minus 31. And then K, that's the kinetic energy, which is the 1 kiloelectron volt. So that's 1000 electron volts, which is 1000 times 1.602 times 10 to the minus 19 joules. And we can now solve this on the calculator. When we do that, we get 3.88 times 10 to the minus 11 meters. And so we can write this in nanometers if we want. Because it's an electron, we'd expect its wavelength to be less than the wavelength of visible light. So this is equal to 0.0388 nanometers. Part B, we've then got a photon in this case. So for a photon, we don't have a mass here. So we can't use this same expression here. But for a photon, we know that E is equal to HF, and we know that F is equal to C over lambda. So this is equal to HC over lambda. So this tells us that lambda is equal to HC on E, which we can substitute in for. So we've got 6.626 times 10 to the minus 34 times 3 times 10 to the 8 over our energy, which is 1 kiloelectron volts, so 1000 electron volts. And then to get it into joules, we multiply it by the charge on an electron. And solving this, we get this is equal to 1.24 times 10 to the minus 9 meters, which is equal to 1.24 nanometers. And then C, we've now got a neutron with the same energy. So a neutron again has mass, so we're going to use this equation again. So lambda is equal to h over the square root of 2mk. So that's equal to 6.626 times 10 to the minus 34 over the square root of 2. Now the mass of a neutron is equal to 1.675 times 10 to the minus 27 times 1000 times 1.602 times 10 to the minus 19. And solving this, we get 9.04 times 10 to the minus 13 meters, which if we want, we can write as 0.904 picometers. Okay. Problem 9. Now, this is an uncertainty principle one. We're told that the average lifetime of a muon is 2 microseconds, and to estimate the minimum uncertainty in the rest energy of a muon. So we can use that the uncertainty in the energy times the uncertainty in the time has got to be greater than or equal to h bar on 2. Okay, so h bar on, well, let's rearrange it. So we know the maximum uncertainty in the time, that's approximately the lifetime. And so we have the uncertainty in the energy has to be greater than or equal to h bar on 2 times delta t, where this is the lifetime. And so this is equal to 6.626 times 10 to the minus 34. That's h, and then h bar is equal to h over 2 pi. So then we divide by 2 pi, and then on the bottom we've got this factor of 2, and the lifetime we're told is 2 microseconds, so that's 2 times 10 to the minus 6. And so solving this on the calculator, we get 2.6 times 10 to the minus 29 joules. So that's equal to 3 times 10 to the minus 29 joules. And then if we want to give it in electron volts, we just divide by the charge on an electron, 1.602 times 10 to the minus 19, and this gives us around about 2 times 10 to the minus 10 electron volts. So we're only giving these to one significant figure, as delta T was only given to one significant figure, and because this is talking about uncertainties, it doesn't make much sense to give too many significant figures anyway. This is problem 10. So in this problem, we've got a block with a mass of 0.500 kilograms at rest on a pond. The location is known to a precision of 0.150 centimeters. So we know its location with an uncertainty of 0.150 centimeters. And we're asked what's the minimum uncertainty in the box speed. So we need to find this. So this is another Heisenberg uncertainty problem. So we know that delta x, delta p is greater than or equal to h bar on 2. And we know that p is equal to mv. So the uncertainty in p, if the mass is known exactly, comes down to just the uncertainty in v. So we can write this as the mass times delta v. So we've got delta x times m delta v is greater than or equal to h bar on 2. So delta v is greater than or equal to h bar over 2 times m times delta x. So this is equal to 6.626 times 10 to the minus 34. H bar, so we're dividing by 2 pi. We've got our factor of 2. We've got our mass, which is the 0.500 kilograms. And then we've got our uncertainty in x, which is 0.150. Now that's centimeters. So to get it to meters, we times it by 10 to the minus 2. So solving this on the calculator, we end up with 7.03 times 10 to the minus 32 meters per second. This is a very, very, very small number, so that implies that we do know its speed very accurately, or at least we can know its speed very accurately. We're not limited much at all by Heisenberg's uncertainty principle.